There is a sentence written somewhere in the universe that no one will ever read again. Not because it was destroyed, because it fell into a black hole, and the black hole, in the fullness of time, will simply evaporate away into a faint warmth, leaving nothing behind that remembers the sentence was ever there. That is the trouble. Physics has one rule it has never been willing to break, older and more stubborn than almost any other, which says that the past is always recoverable from the present, that nothing is ever truly erased, that the universe keeps every receipt. Black holes appear to tear that rule in half. And for 50 years, some of the most careful minds alive have been standing at the edge of that tier, trying to work out whether the universe is a place that forgets. This is the story of that question. It moves slowly because it has to. It begins with a star that ran out of fuel, and it ends somewhere past the last light in the cosmos, in a darkness so long and so quiet that the word patience stops meaning anything at all. Begin with the dark itself. Space is not empty, but it is close. Between the stars, there drifts a thin haze of hydrogen, perhaps 1 atom per cubic centimeter, colder than almost anything a laboratory has ever made. Light crosses it without noticing. And scattered through that haze, at distances that make the word distance feel small, there are objects that do not shine. They have no surface. They have no material to speak of. They are not made of anything in the way a rock is made of minerals, or a star is made of plasma. They are made of geometry. They are places where the shape of space and time has folded so steeply inward that every path leading outward has quietly closed, the way a road closes when the ground beneath it falls away. Astronomers call them black holes. The name is younger than the idea, and both are younger than the trouble they cause. The idea came first, in the 18th century, from an English clergyman with a telescope and an unusual habit of following an argument wherever it went. His name was John Michell, rector of Thornhill in Yorkshire, and in the year 1783, he wrote a letter to the Royal Society that contained something no one had quite said before. Michell knew that a cannonball fired upward from the earth would fall back unless it was fired fast enough. He knew that the speed required, the escape velocity, depended on how much mass the world had and how tightly that mass was packed. And he knew, from Isaac Newton, that light was thought to be made of small corpuscles, tiny particles streaming outward from luminous bodies. So he asked what would happen to a star so massive and so compact that its escape velocity exceeded the speed of light. The answer followed with an almost embarrassing simplicity. The light would rise, slow, and fall back. The star would still be there, still burning, still enormous, and it would be invisible. He called such an object a dark star. He even suggested how one might be found by watching a visible companion star swing around an unseen partner, which is very nearly how the first black hole candidates would, in fact, be found 2 centuries later. 13 years afterward, in France, Pierre-Simon Laplace arrived at the same conclusion independently and put it into his book on the system of the world. Then he took it out again in a later edition, quietly, without much explanation. The wave theory of light was rising, and a wave did not obviously have to obey the arithmetic of falling cannonballs. The dark stars slipped out of the conversation for more than 100 years. They came back through a different door. In November of 1915, Albert Einstein finished the general theory of relativity, which said that gravity is not a force pulling across space, but a curvature of space and time itself. Mass tells the geometry how to bend. The geometry tells the mass how to move. The equations were beautiful, and they were also formidable, a set of coupled nonlinear relations that Einstein himself doubted would ever be solved exactly for anything realistic. Within weeks, someone solved them. Karl Schwarzschild was a German astrophysicist serving on the Russian front, calculating artillery trajectories. Ill with a rare autoimmune skin disease that would kill him within months, he read Einstein's paper in the trenches. He found the exact solution for the geometry outside a spherical, non-rotating mass, wrote it up, and sent it to Einstein, who read it to the Prussian Academy on Schwarzschild's behalf in January of 1916. Schwarzschild died that May at the age of 42. His solution contained something strange. At a particular radius, which depends only on the mass, the mathematics became peculiar. Certain terms blew up. For the Sun, that radius works out to a little under 3 kilometers, roughly 2 miles. For the Earth, it is about 9 millimeters, smaller than a marble. Since no real star came anywhere near being packed that tightly, the peculiar radius seemed like a curiosity, a place where the coordinates misbehaved, and nature never went. It took decades to understand that the misbehavior was in the coordinates, not in the space. The geometry there is perfectly smooth. Nothing dramatic happens locally. What happens is subtler and far worse. At that radius, called the Schwarzschild radius, the future itself tilts. Every direction that a thing might travel, every possible path forward in time, leads inward. Not because something is pulling, because outward has stopped being a direction that exists. Moving away from the center becomes as impossible as moving into yesterday. That surface is now called the event horizon. It has no substance. A person crossing it would feel nothing, notice nothing, see no wall, and hear no sound. For a sufficiently large black hole, the tidal stretching at the horizon is gentler than the difference in gravity between a person's head and feet standing on Earth. And yet a line has been crossed that cannot be uncrossed, and everything after it is one way. In 1939, J. Robert Oppenheimer and his student Hartland Snyder published a short paper on what they called continued gravitational contraction. They showed that if a sufficiently massive star exhausted its nuclear fuel and no known pressure could hold it up, it would not settle into some final compressed lump. It would keep falling. It would fall past its own Schwarzschild radius and go on falling. And to an observer watching from outside, the collapse would appear to slow and freeze and dim and redden until the star simply faded from view. Its light stretched into wavelengths too long to catch. The paper appeared on the 1st of September 1939, the same day Germany invaded Poland. The world had other things to read. For nearly 30 years, the subject drifted at the margins. Then, in the 1960s, a combination of new mathematics and new observations pulled it back to the center. Roy Kerr, a New Zealander, found the exact solution for a rotating collapsed object in 1963, which mattered enormously because everything in the universe rotates. Roger Penrose introduced techniques from topology that proved the collapse was not an artifact of assuming perfect symmetry. That real, lumpy, imperfect stars would collapse to a singular condition too. Quasars were discovered, blazing beacons at cosmological distances that seemed to require an engine of impossible compactness. And the physicist John Archibald Wheeler, who had a gift for language that matched his gift for physics, began using a term that had been floating in conversation. In 1967, in a talk in New York, He called them black holes, and the name held because it was short and because it was true. Now the geometry has a name. The next thing to understand is what it does to the things that fall in. And to do that, one has to understand what physicists mean by the word information, which is not what anyone else means by it. Information in physics has nothing to do with meaning. A love letter, a shopping list, and a page of random characters all carry the same amount of it if they have the same number of symbols. Information is not the message. Information is the specification. It is the complete list of details that distinguishes one particular arrangement of the world from every other arrangement it might have had. Consider a book. Burn it. The meaning is lost in any practical sense. The reading of it is lost, but the physics is stubborn on this point. The smoke and the ash and the heat and the light that left the fire are all still there, dispersed, scrambled beyond any hope of practical recovery, but not gone. Every molecule of that smoke is moving along a path determined by the collisions that came before. Every photon that left the flame carries a history. If a being existed who could measure the position and velocity of every particle in the room with perfect precision, and who knew the laws of motion exactly, that being could, in principle, run the calculation backward. The smoke would rise back into the flame. The ash would knit itself into paper. The letters would reassemble on the page, and the book would be readable again. This is not a poetic claim. It is a structural feature of every fundamental theory of physics that has ever been written down. In classical mechanics, it follows from the fact that the equations of motion are reversible in time, that a movie of colliding billiard balls run backward shows a physically legal set of collisions. In quantum mechanics, it goes by the name unitarity, and it is built into the machinery at the deepest level. The quantum state of a system evolves by a rule that preserves the total probability and preserves the distinguishability of different starting conditions. Two different beginnings must lead to two different endings. Always. If they could lead to the same ending, then looking at the ending would not tell you which beginning had occurred, and the past would have been deleted. The reason this matters so much is that it is the source of all predictive power. If the present does not carry a full record of the past, then the future does not carry a full record of the present, and physics stops being able to say what will happen. The whole enterprise rests on the quiet assumption that the universe never loses track. There is a way to make the assumption vivid. Take the observable universe, all of it, every galaxy and every grain of dust, and every neutrino streaming through every star. In principle, according to quantum mechanics, that entire arrangement is described by a single mathematical object, a wave function, and that object evolves smoothly and reversibly forever. Nothing is added, nothing is subtracted. The universe does not create information, and it does not destroy it. It only shuffles it, endlessly, into arrangements too tangled for anyone to read. The word for that tangling is entropy. Entropy is often described as disorder, which is a rough translation and a slightly misleading one. A better way to hold it is this. Entropy measures how many different microscopic arrangements would look identical from the outside. A shuffled deck of cards has high entropy not because it is messy, but because there are 80 billion trillion ways to shuffle a deck, and only one way to have it sorted. When something becomes more disordered, no information vanishes. It simply migrates from the large scale, where it can be seen, to the small scale, where it cannot. The book that burned did not lose its information. Its information became the precise wiggle of 10,000 trillion molecules of smoke. The second law of thermodynamics says entropy never decreases in a closed system. It is the only law of physics that knows which way time runs, and it holds everywhere in every experiment without exception. Except, perhaps, near a black hole. And this is where the trouble begins in earnest, and it began with a teacup. The story is told by John Wheeler, who in the late 1960s was thinking about the strange perfection of the objects he had named. General relativity made a remarkable claim about them. A black hole, once it has settled down, is described completely by three numbers: its mass, its electric charge, its angular momentum, which is to say how fast it spins. That is all, not a fourth number, not a footnote, not a trace of what went in. This is the no-hair theorem, and the name comes from Wheeler again, who said that black holes have no hair, meaning no distinguishing features, nothing to grab onto. The mathematics behind it was assembled through the late 1960s and into the 1970s by Werner Israel, who proved the non-rotating case, and Brandon Carter and David Robinson, who handled the rotating one, with an important contribution from Richard Price, who showed the mechanism by which the hair falls out. Any bump, any lump, any irregularity in a collapsing star radiates away as gravitational waves during the collapse itself, in a fraction of a second, leaving a surface of impossible smoothness behind. So a black hole made from a collapsed star, and a black hole made from an equal mass of antimatter, and a black hole made from an equal mass of encyclopedias, and a black hole made from an equal mass of pure light are the same black hole, identical in every measurable respect. There is no experiment from the outside that could tell them apart. Wheeler's teacup follows directly. Suppose a person takes a cup of hot tea, which has a certain entropy, a certain amount of hidden microscopic disorder in the jostling of its molecules, and drops it over the horizon of a black hole. The tea is gone. Its entropy is gone with it. The outside universe now contains less entropy than it did a moment before. The second law, the one law that had never failed, has just been violated by the simple act of tidying up. Wheeler put this to a graduate student named Jacob Bekenstein, apparently in a somewhat teasing spirit, as a puzzle to chew on. He said something to the effect that he felt like a criminal because he had committed a crime, and the evidence was gone forever. Bekenstein took it seriously. He was 25 years old. His reasoning ran like this: if the second law is truly fundamental, and it seems to be, then the entropy cannot have disappeared. It must have gone into the black hole, which means the black hole must have entropy, which means there is a number attached to a black hole beyond the three that general relativity allows. That counts something. But entropy counts arrangements, and it is not clear what a black hole could possibly be arranging. It has no parts. It has no structure. It has three numbers and a surface. Bekenstein noticed something else, something that had been proved by Stephen Hawking in 1971, and that seemed at first like a mere technical result. The area of a black hole's event horizon never decreases. Throw something in, and the area grows. Collide two black holes, and the area of the result exceeds the sum of the areas that went in. Under every process anyone could construct, that area went up and never down. It behaved, in other words, exactly like entropy. So Bekenstein proposed, in 1972, and more fully in 1973, that the entropy of a black hole is proportional to the area of its horizon, not its volume, which is what anyone would have guessed, since entropy in ordinary matter scales with how much stuff there is, and stuff fills volume. The area, the skin. The proposal was not well received. It was, in fact, considered by most of the field to be wrong, and the person who considered it most wrong was Hawking himself. The objection was simple, and it looked fatal. Entropy and temperature are joined at the hip in thermodynamics. If a thing has entropy and it has energy, then it has a temperature, and the relationship between them is fixed. And anything with a temperature above absolute zero radiates. That is what temperature means. A warm object glows, even if the glow is far into the infrared and invisible to the eye. A black hole cannot glow. Nothing comes out. That is the entire definition. So a black hole must have zero temperature. And if it has zero temperature, it cannot have entropy, and Bekenstein was mistaken, and the teacup remained a crime with no evidence. In 1973, Hawking, together with Brandon Carter and James Bardeen, published a paper laying out 4 laws of black hole mechanics that mirrored the 4 laws of thermodynamics with an almost suspicious precision. Surface gravity played the role of temperature. The horizon area played the role of entropy. The correspondence was exact, term for term, and the authors were careful to say in print that the resemblance was formal, an analogy, a mathematical coincidence, and that black hole temperature and black hole entropy were not real. Hawking set out to prove it. He was, by his own later account, annoyed by Bekenstein, and he wanted to close the matter properly by doing the hard calculation nobody had done. He wanted to work out how quantum fields behave in the curved space around a collapsing star. The calculation took the better part of a year, and when it came out, it said the opposite of what he had expected. To follow what he found, one has to accept something about the vacuum that is not intuitive, but is very well established. Empty space is not empty. In quantum field theory, every point in space is filled with fields, and those fields are never perfectly still. They cannot be. The uncertainty principle forbids a field from having both a definite value and a definite rate of change, which means that even at the lowest possible energy, the field jitters. This jitter is not a metaphor. It has been measured. It shifts the energy levels of hydrogen atoms by an amount that was detected in 1947. It exerts a faint pressure between 2 metal plates held very close together, a pressure predicted by Hendrik Casimir in 1948 and measured in the laboratory since. The jitter can be described, loosely, as pairs of particles flickering into existence and vanishing again, borrowing energy from nothing and returning it before the universe has time to notice. The picture is a cartoon, and every serious physicist will say so, but it is a cartoon that captures something real. The vacuum is a seething thing, and its seething is exactly balanced, so that on average it comes to nothing. Now put that seething vacuum next to a horizon. The horizon is a one-way surface. The pairs that flicker into being near it do not always both flicker out again, because sometimes one of the two falls in before they can meet and cancel. The other is left outside with nowhere to go and nothing to annihilate against. It becomes real. It flies away. And because the total energy has to balance, the one that fell in carries negative energy inward, and the black hole loses a small amount of mass. The black hole glows. Hawking published the result in Nature in 1974, under a title with a question mark in it, and then in fuller form in 1975 in a paper called Particle Creation by Black Holes, which is one of the most cited papers in the history of the subject. The radiation is now called Hawking radiation, and the reaction to it, once the initial disbelief passed, was something close to relief. It rescued Bekenstein. It made the analogy real. Black holes have a temperature after all, and the temperature is exactly what the four laws had implied it should be. And the entropy is exactly 1/4 of the horizon area measured in units of the Planck area. And the factor of 1/4, which no one could have guessed, fell out of the calculation on its own. The Planck area is a very small thing. It is roughly 2.6 times 10 to the negative 70th of a square meter. To have a sense of the scale, a single proton has a cross-section something like 10 to the 40th times larger. The entropy of a black hole, then, is the number of Planck-sized patches that would tile its horizon, divided by 4. For a black hole the mass of the Sun, that number comes out to about 10 to the 77th in the natural units physicists use. The Sun itself, as a ball of hot plasma with all its churning and all its jostling, has an entropy of about 10 to the 58th. Collapse the Sun into a black hole, and its entropy jumps by 19 orders of magnitude. Black holes are not merely disordered. They are the most disordered objects that can exist. Pack any amount of mass and energy into any region of space, and the maximum entropy that region can hold is achieved when it collapses into a black hole. Nothing can hide more from the outside than a black hole does. The temperature, on the other hand, is almost nothing. This is the detail that makes the whole subject so difficult to check. Temperature runs inversely with mass. The bigger the black hole, the colder it is. For a black hole the mass of the Sun, the temperature is around 60 billionths of a Kelvin above absolute zero. The cosmic microwave background, the cold afterglow of the early universe that fills all of space, sits at about 2.7 Kelvin, which is 40 million times warmer. A stellar mass black hole today is therefore not evaporating at all. It is absorbing more from the background radiation than it emits. It is growing. Only when the universe has expanded enough for the background to cool below the black hole's temperature can evaporation begin in earnest. And for a black hole the mass of the Sun, that will take on the order of 100 trillion years, which is roughly 10,000 times the present age of everything. The universe is barely getting started, but the number that matters most is the one at the end. The evaporation time for a black hole the mass of the Sun, once it begins, is on the order of 10 to the 67th years. The number is so large that it does not connect to anything. It is not a long time in any sense that a person can hold. It is simply an arrangement of digits, and yet it is finite. That is the whole point. It ends, which brings the paradox into view. Hawking's calculation gave more than a temperature. It gave a character to the radiation, and the character was the trouble. The radiation is thermal, perfectly thermal. It is the same radiation that any warm body emits, a smooth, featureless spectrum determined by a single number, the temperature, and by nothing else at all. It carries no imprint of what fell in. It is, in the technical sense, maximally random. That is not obviously alarming until one follows it to the end. The black hole shrinks as it radiates. As it shrinks, it gets hotter because temperature runs inversely with mass, so the process accelerates. Over almost all of its life, the shrinking is imperceptibly slow. In the final second, the last few thousand tons go all at once, in a burst of gamma rays with the energy of several million tons of high explosive. And then nothing. The horizon closes on itself and is gone. Where the black hole was, there is flat, empty space, and a great deal of thermal radiation drifting outward, radiation which carries the same information whether the hole was made from stars, or from encyclopedias, or from an equal mass of pure light. Everything that fell in is gone, not scrambled, not hidden. Gone. Hawking published this conclusion in 1976 in a paper titled Breakdown of Predictability in Gravitational Collapse, and he did not present it as a puzzle to be solved. He presented it as a discovery. His position, held firmly for the next 28 years, was that quantum mechanics is simply wrong in the presence of a horizon. Information really is destroyed. The universe really does forget. Physics would have to be rewritten to allow it, and he proposed a way to rewrite it, replacing the quantum mechanical rule that maps a starting state to an ending state with a coarser rule that maps a starting state to a probability distribution over ending states, losing precision irreversibly along the way. Most of the general relativity community found this reasonable. Most of the particle physics community found it appalling. And the split was not merely a matter of taste. Each side was defending the deepest principle of its own field, and the two principles could not both be right. The relativists said the following: the horizon is not special. It is a perfectly ordinary place. A person falling through it notices nothing unusual. General relativity says that once a thing has crossed, no signal it emits can ever reach the outside, and there is no wiggle room in that statement. It follows from the geometry as directly as anything follows from anything. So information that crosses the horizon cannot come back out, and if the black hole subsequently disappears, that information has nowhere left to be. The conclusion is not comfortable, but it is forced. The particle physicists said the following: unitarity is not a convenience. It is the structural spine of quantum mechanics. Give it up, and probabilities stop summing to one. Give it up, and energy conservation goes with it. Because the same mathematics that guarantees one guarantees the other. Several people worked out what a small amount of information loss would do to ordinary physics if it were allowed to happen at all, and the answer was catastrophic. Leonard Susskind, Tom Banks, and Michael Peskin showed in the mid-1980s that a theory permitting information to leak away would inject energy into everything, everywhere, heating the vacuum to temperatures that would have boiled the universe long ago. Empty space would glow. It does not glow. So information is not lost, and Hawking's calculation, however careful, must be missing something. Both arguments are good. That is what makes it a paradox rather than a mistake. A mistake is when someone does the arithmetic wrong. A paradox is when two things that must both be true cannot both be true, which means that some assumption so obvious that nobody wrote it down is quietly false. In 1997, Hawking and Kip Thorne made a formal bet with John Preskill, a theorist at Caltech. Hawking and Thorne wagered that information is destroyed. Preskill wagered that it is not. The stakes were an encyclopedia of the winner's choosing, from which information could be recovered at will, which was the joke. The bet was written out and signed. In the tradition Thorne and Hawking had built over the years of betting each other on things they could not yet prove. It would take 7 years to settle, and even then, not everyone would agree it was settled. The years in between were not idle. They were full of proposals, and it is worth walking through them slowly, because each one is an attempt to find the hidden assumption, and each one fails in an instructive way. The first proposal was the simplest. Perhaps the black hole does not evaporate completely. Perhaps, when it shrinks down to something near the Planck mass, which is a very small mass by cosmic standards, but a very large one by particle standards, about the mass of a flea's egg concentrated into a region far smaller than a proton, the evaporation stops. Quantum gravity takes over, whatever quantum gravity is, and what remains is a stable remnant. The information is still inside it. Nothing was lost. The universe is merely littered with tiny sealed vaults. It is an appealing thought, and it does not survive contact with counting. The problem is that black holes come in every size, and a large black hole holds an enormous amount of information. And if all of that information has to fit into a remnant of fixed tiny size, then remnants must come in an infinite variety of internal states, while all having essentially the same mass and the same external appearance. That means there are infinitely many distinct particle species that all look identical from outside and all weigh about the same. In quantum field theory, any species of particle that can exist will be produced, at some rate, in any sufficiently energetic process. Infinitely many species means an infinite production rate. Every collision anywhere would be spraying remnants. Every patch of vacuum would be unstable. The universe visibly does not do this. The remnant idea has been revisited many times, with cleverer versions each time, and it has never quite died. But it has never quite lived either. The second proposal was stranger, and it came from Hawking himself, among others. Perhaps the information is not lost, exactly. Perhaps it goes somewhere. Perhaps the interior of the black hole pinches off from the rest of spacetime as the whole evaporates, budding away into a separate universe of its own, a baby universe, carrying everything that fell in with it. From the outside, it looks like information loss. From a larger view, it is only information relocation. The book still exists. It is simply in a room that no longer connects to any hallway. This is not obviously wrong, and it is not obviously anything, which is the difficulty. A statement that can never be checked from any accessible vantage point sits awkwardly in physics, and on closer analysis, the baby universe scenario turned out to have the same problems as remnants, since, from the perspective of the parent universe, an unreachable baby universe and a sealed vault are the same object with different names. The third proposal was the one that eventually won, and it took 30 years to make it respectable. Perhaps the information comes back out. Perhaps it is encoded in the Hawking radiation after all, in correlations so subtle that Hawking's original calculation, which was an approximation, simply could not see them. The analogy usually offered is the burning book, and it is a good analogy as far as it goes. The radiation from a burning book also looks thermal. Measure the light coming off a fire with any ordinary instrument, and it is a smooth spectrum, featureless, characterized by temperature alone. And yet the information is in there, hidden in the delicate correlations between one photon and the next, between the photon and the smoke, between the smoke and the ash. Nobody can read it, but it is not gone. The trouble with the analogy is that a book has a surface and an inside made of the same stuff, and the light leaving the fire is in contact with the letters on the page. That is how it picks up the imprint. A black hole's radiation is created outside the horizon, in the vacuum, in a region that has never touched anything that fell in and never will. The information is on the wrong side of a one-way wall. There is no mechanism. Saying the information comes out in correlations is not a solution. It is a statement of what a solution would have to accomplish. To make it work, someone would have to find a reason why the inside of a black hole is not really separate from the outside, which sounds like nonsense, and is, roughly speaking, what turned out to be true. The first crack came from a direction nobody was watching, and it came from thinking hard about the entropy formula. Recall that black hole entropy scales with area, not volume. Physicists had accepted this as a fact about black holes and moved on. Gerard T. Hooft, a Dutch theorist who had already won a share of a Nobel Prize for work on the mathematics of the Standard Model, stopped and looked at it directly in 1993, and Leonard Susskind sharpened the idea in 1994. And what they said was this: a black hole is the most entropic thing that can occupy a region of space. Its entropy is set by its surface area. Therefore, the maximum information that can be stored in any region of space, by anything, is set not by the volume of the region, but by the area of its boundary. If a person tried to build a library dense enough to violate that bound, the library would collapse into a black hole before the last book was shelved, and the resulting hole would hold less than the library was supposed to. This is deeply peculiar. It says that the world is not what it appears to be. A room has a volume, and the volume feels like the place where things are. But the accounting says the room's contents can be fully specified by data written on its walls, at a density of about 1 bit per Planck area, which is roughly 10 to the 69th bits per square meter. The interior is not an independent thing. The interior is a projection. They called it the holographic principle, after the optical holograms that store a three-dimensional image in a two-dimensional film. And for several years, it was a slogan without a theory. It sounded profound. It also sounded like it might be nothing. Then, in 1997, Juan Maldacena, working at Harvard, wrote down something that made it concrete. Maldacena was studying string theory, and he found a correspondence between two theories that have no business being related. On one side, a theory of gravity, with strings and curved space and black holes, living in a particular kind of universe called anti-de Sitter space, which is a space with a constant negative curvature, and a boundary at infinity that light can reach and return from in finite time. On the other side, a theory with no gravity at all, an ordinary quantum field theory of the kind used to describe particles in a laboratory, living on the boundary of that space, one dimension lower. His claim was not that the two are similar. His claim was that they are the same theory. Every event in the interior, every gravitational effect, every black hole, corresponds to something happening in the boundary theory. The dictionary is complicated, and much of it is still being written. But the correspondence has been checked in a great many independent ways over almost 30 years, and it has held every time. It is now the single most cited result in theoretical physics. The implication for the paradox is immediate and enormous. The boundary theory is an ordinary quantum theory. Ordinary quantum theories are unitary. They cannot lose information. There is no mechanism for it and no room for it. So if a black hole forms in the interior and evaporates completely, and if the two descriptions really are the same physics, then no information was lost in the interior either. It cannot have been. The bookkeeping on the boundary would not allow it. This is an existence proof, and it settled a great many minds. But it is a peculiar kind of proof, because it says only that the information gets out. It does not say how. It is as if a person had proved, by an argument about conservation of mass, that the magician did not really make the rabbit vanish, without having any idea where the rabbit is. Meanwhile, another idea had appeared in 1993 from Susskind together with Lars Thorlacius and John Uglum, and it was as strange as anything in the subject. They called it black hole complementarity. Their observation started with a question about double counting. Suppose an object falls into a black hole. From the outside, the object approaches the horizon, slows, reddens, and appears to smear across the surface. Its light stretched to longer and longer wavelengths until it fades. It never quite crosses from the outside view, because the crossing takes infinite time as measured from far away. Then, much later, the black hole radiates the object's information back out. From the outside, the object was never inside. It sat on the horizon, got hot, and eventually evaporated back off. From the object's own perspective, none of that happened. It crossed the horizon at a definite moment on its own clock, felt nothing, and continued inward toward the center. It was never smeared on any surface. It was never radiated. Both accounts cannot be true. The object is either inside or outside. It is either a copy of the radiation or the original in the interior. Quantum mechanics forbids copying an unknown quantum state, a result called the no-cloning theorem, and here there appear to be two copies. Complementarity says the contradiction is not real because no observer can ever check it. The outside observer can never see the interior. The infalling observer can never report back. To catch the universe in a lie, someone would have to gather the radiation, extract the information, and then dive in and compare it against the original. Susskind and his collaborators worked out how long that would take, and the answer is that the black hole would have to radiate away roughly half its entropy first. And by the time the diver reached the interior with the extracted copy in hand, the original would have long since hit the center. The comparison cannot be made, and a contradiction that no possible observation can reveal, they argued, is not a contradiction. It is two descriptions of one thing, valid in different frames, like the two accounts of a moving clock in special relativity. It is an uncomfortable resolution. It gives up on the idea that there is a single objective account of where things are. But it is not obviously wrong, and it hung in the air for 2 decades. Then there is the matter of when. Not how, but when. And this turned out to be the sharpest tool anyone had. Don Page, who had been Hawking's student, and who once lived in the Hawking household as a postdoctoral assistant, asked a question in 1993 that nobody had thought to ask so precisely. He wanted to know, supposing the information does come out, on what schedule it comes out. He was not proposing a mechanism. He was doing accounting, using nothing but the general rules of quantum information theory, which apply to any unitary process whatsoever. His reasoning goes like this. Track the entanglement entropy of the radiation, meaning a measure of how correlated the radiation is with whatever remains behind. At the beginning, before any radiation, there is none. The radiation does not exist. As the first photons trickle out, each one is entangled with a partner that fell in, so the entropy of the radiation climbs. If Hawking's picture were exactly right, it would keep climbing until the black hole was gone, at which point the radiation would be entangled with nothing at all, which is a mathematical impossibility for a system that started in a definite pure state. That is the paradox restated in the language of information. But if the process is unitary, Page said, something else must happen. The entropy must climb, and then it must turn around and come back down, reaching zero exactly when the black hole vanishes, because at that point the radiation is all there is, and all there is must be back in a definite state. And the turning point, he showed, occurs when the black hole has emitted about half its entropy, which for a black hole of stellar mass happens after a span of time so long that half of 10 to the 67th years is a fair summary of it. That turning point is now called the page time, and the curve of entropy rising and falling is called the page curve, and it became the target. Any correct theory of black hole evaporation has to reproduce it. Hawking's calculation does not. Hawking's calculation gives a line that rises and keeps rising. The gap between that line and the page curve is the paradox, drawn as a picture. Page also worked out something else, almost as an aside, that is quietly astonishing. Before the page time, the radiation carries essentially no recoverable information. It is, for all practical purposes, exactly as random as Hawking said. Only after the halfway point does the information begin to emerge, and then it emerges quickly, each new photon carrying almost a full bit. A young black hole is a vault. An old black hole is a sieve. The transition is not gradual in the way one might expect. It has a moment. In 1999, Patrick Hayden and John Preskill would push this further and find something stranger still. Throw an object into a black hole that is already past its page time, and the information about that object comes back out in the radiation almost immediately, on a timescale set by the scrambling time, which for a black hole the mass of the Sun is a few thousandths of a second. The old black hole acts as a mirror. It reflects, not the light, but the information carried by the light, encoded so thoroughly among the outgoing photons that reading it would require knowing everything about every photon that had ever left, and having a quantum computer of implausible size, and even then it would work. In principle, which is the phrase that does most of the labor in this entire field. By 2004, the weight of the evidence had shifted enough that Hawking changed his mind in public, which he did at a conference in Dublin, in front of a room of specialists and a great many cameras. He said that he had thought about the problem for 30 years, and that he now believed information is preserved, that the horizon is not as absolute as it had seemed once quantum gravity is taken into account, and that a black hole's radiation carries the information out, mangled and unrecognizable, but present. He paid the bet. He gave John Preskill a baseball encyclopedia, chosen for the joke, since information can be retrieved from it at will. He remarked that it might have been kinder to hand over the ashes. Kip Thorne did not concede. He has said since that he was not persuaded by the argument Hawking gave, and the argument was in truth rather thin. It relied on a technical claim about summing over all possible geometries in a quantum calculation, including geometries with no black hole at all, and on the assertion that the contributions from the ones without horizons would eventually dominate and carry the information out. The paper Hawking eventually wrote was short and was not widely regarded as settling anything. It settled a bet. It did not settle a paradox, and within a decade the paradox came back, sharper than before, and it came back from the direction of complementarity, which everyone had assumed was safe. In 2012, 4 physicists at the University of California at Santa Barbara, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, published a paper that was intended as a defense of complementarity and turned out to be a demolition of it. The argument is now called the firewall paradox, and the 4 names are usually compressed into a single acronym that the community pronounces as a word. Their reasoning is a careful piece of bookkeeping about entanglement, and it goes as follows. Entanglement is a relationship between two quantum systems in which neither has a definite state of its own, but the pair together does. It has a property that turns out to be decisive here, called monogamy. A quantum system can be maximally entangled with exactly one partner, not two, not a little bit with each of several. If System A is fully entangled with System B, then A has nothing left over to share with System C. This is a theorem, not a guideline. It follows from the structure of quantum states as directly as anything does. Now consider a black hole that is past its page time, more than halfway evaporated. Consider a single photon of Hawking radiation about to leave. That photon must be entangled with the earlier radiation, all the radiation that left before. It has to be, because that is what the page curve requires. Late radiation carrying information means late radiation is correlated with early radiation. Without that entanglement, the entropy cannot come back down, and unitarity fails. That same photon must also be entangled with its partner, just inside the horizon. It has to be, because that is what makes the horizon a smooth, ordinary place. The vacuum near any point in empty space is a highly entangled thing, with short-range correlations across every surface one might draw. Cut those correlations, and the vacuum is no longer the vacuum. It becomes a violently excited state, seething with real particles at enormous energy. So the photon must be fully entangled with the early radiation and fully entangled with its interior partner. Monogamy says it cannot be both. Something has to give, and the authors went through the options one by one. Give up unitarity, and Hawking was right all along, and quantum mechanics is broken. Give up the page curve, which is the same thing. Give up complementarity, which is what they had been trying to save. Or give up the smoothness of the horizon. That last one is what gave the paper its name. If the entanglement between the outgoing photon and its interior partner is severed, then the vacuum at the horizon is not the vacuum. It is a wall of radiation at enormous energy, and anything falling in does not drift gently across a place where nothing seems to happen. It strikes something. It is destroyed at the boundary, incinerated by high-energy quanta, and there is no interior experience at all because there is no one left to have it. A firewall. This is a catastrophe for general relativity, and not a small one. Einstein's theory rests on the equivalence principle, the observation that a freely falling observer feels nothing, that gravity can always be transformed away locally by falling with it. It was the insight that started everything, the one Einstein called the happiest thought of his life. The horizon of a large black hole is a place with very weak curvature. Nothing in general relativity permits anything to happen there. A firewall at the horizon means the equivalence principle fails, not in some extreme regime of enormous curvature where everyone expected it to fail, but in a perfectly gentle region of ordinary space. The paper landed hard. It was not a fringe claim, and it was not easily dismissed. The argument used only well-established results, applied carefully, and it produced a conclusion that everyone hated. This is the signature of a real paradox rather than an error. The years after it were loud, by the standards of a quiet field. Conferences were organized around it, proposals multiplied, and out of that noise came an idea from Juan Maldacena and Leonard Susskind. In 2013, That is either the deepest thing anyone has said about this, or a very elegant coincidence, and the jury remains out. They notice that two of Einstein's papers from 1935, written in the same year with different collaborators, might be describing the same thing. In one, with Nathan Rosen, Einstein wrote down a solution containing a bridge connecting two regions of spacetime, a throat joining two black holes. It is now called an Einstein-Rosen bridge, or more commonly a wormhole, a word Wheeler supplied later. It is not traversable. Nothing can pass through. The throat pinches off faster than light could cross it, so the two mouths are connected geometrically without being connected causally. In the other, with Boris Podolsky and Rosen again, Einstein described the phenomenon he found so objectionable that he intended the paper as a refutation of quantum mechanics. Two particles prepared together, separated by any distance, share a state that cannot be assigned to either alone. Entanglement. Maldacena and Susskind proposed that these are the same phenomenon. The two entangled black holes are, in the interior geometry, connected by a wormhole. That entanglement and geometric connection are two descriptions of one underlying fact. They wrote it as a slogan, and the slogan has stuck. The consequence for firewalls is that the entanglement between an outgoing photon and the early radiation would not be a separate relationship, competing with the entanglement to the interior partner. It would be the same relationship, seen through a bridge. The interior partner and the early radiation would not be two things. The early radiation, scattered across a vast volume of space, would in some sense be the interior. Monogamy would not be violated because there is only one partner, wearing two descriptions. It is a beautiful idea. It has not been proved. It has generated a great deal of work and a great deal of doubt, and the honest summary is that it points somewhere true without anyone yet being able to say where. Around the same time, from a different direction, Hawking returned to the problem one final time in the last years of his life with Malcolm Perry and Andrew Strominger. Their paper in 2016 was titled Soft Hair on Black Holes. The no-hair theorem, they argued, is not quite right. It is right about the obvious hair. It misses something subtle. The vacuum of a gauge theory, including gravity, is not unique. There are infinitely many vacua, differing from one another by the emission of what are called soft particles, quanta of zero energy. Zero-energy quanta do not cost anything to make and do not show up in any measurement of the mass, charge, or spin. But they change the state. And when a particle falls into a black hole, it deposits soft hair on the horizon, a pattern of these zero-energy excitations, a fingerprint that is invisible to every classical measurement. The proposal is that the information is stored in that fingerprint and released as the whole evaporates. The idea was received with real interest and also real skepticism. It is not clear that soft hair can carry enough information to do the job. Counting arguments suggest it may fall far short of the 10 to the 77th states a solar mass black hole requires. Work continues. Hawking died in March of 2018, a few days after finishing a related paper. The problem he had opened in 1976 was still open when he left it. And then in 2019, something happened that has changed the shape of the field, though not the shape of the mystery. Two groups, working separately, calculated the page curve. Not assumed it, calculated it from a gravitational theory, using the tools of general relativity itself, and got the curve to bend. Jeff Pennington, then at Stanford, was one. Ahmed Almeri, one of the original Firewall authors, working with Netta Engelhart, Donald Marolf, and Henry Maxfield, was the other. And what they found, and what a larger set of collaborators, including Pennington, Stephen Schenker, Douglas Stanford, and Zhenbin Yang, made more rigorous the following year with a method involving what are called replica wormholes, was that the calculation had been incomplete in a way nobody had suspected. The technical statement involves a rule for computing entropy in a gravitational theory, which says that the entropy of a region is given by the area of a certain surface, chosen by a minimizing procedure among all the candidate surfaces available. The rule descends from work by Shinsei Ryu and Tadashi Takeyanagi in 2006, and was refined by others over the following decade. The key point is that it is a minimizing procedure, and a minimizing procedure can change its answer suddenly when a new candidate appears that was not there before, and a new candidate does appear right around the page time. At early times, the minimizing surface is trivial, and the entropy of the radiation just climbs, exactly as Hawking said. But past the halfway point, a different surface becomes available, sitting just inside the horizon, and it gives a smaller answer. The rule takes the smaller answer. The entropy turns around and comes down. The consequence of taking that surface is the strange part. It means that when one computes the entropy of the radiation drifting far from the black hole, the correct calculation includes a region of the black hole's interior, not adjacent to the radiation, not connected to it by any path through space. A disconnected patch of the interior counts in the accounting as part of the radiation. These patches are called islands, and their existence says that the interior of an old black hole is not a separate place at all. It is encoded, redundantly and non-locally, in the radiation that has already left. The radiation is not a copy of the interior. It is the interior, described in a coordinate system that does not look like space. The page curve comes out right. The paradox, in the narrow technical sense of a contradiction between two calculations, is resolved. Gravity, correctly computed, is unitary. Hawking's calculation was not wrong so much as it was blind to a contribution that only matters after the halfway point, a contribution invisible in the approximation he was using and visible only when the sum over geometries is done more completely. This is a real result, and it is a beautiful one, and it deserves to be celebrated. And it should also be described honestly, which means describing what it does not do. It does not explain how the information gets out. The island calculation is a piece of bookkeeping. It shows that the books balance. It does not show the mechanism by which a bit of information about a page of an encyclopedia, having crossed a horizon, comes to be encoded in an outgoing photon. The rule that produces the right answer was, in a sense, imported from the boundary theory, where unitarity was never in doubt, and the achievement is that the gravitational calculation now agrees with it. That is a great deal. It is not everything. It also relies on techniques whose validity in our own universe is not established. The strongest versions of the argument live in anti-de Sitter space, which has a constant negative curvature and a boundary that light can reach. Our universe has a small positive curvature and no such boundary. The tools do not obviously carry over. Whether they do is one of the live questions in the subject, and it does not tell anyone what a black hole's interior actually is. The island story says the interior is somehow made of radiation. It does not say what happens to a person who falls in, or what they see, or whether their experience is real in the way ordinary experience is real, or in what sense they continue to exist once the black hole they are inside has finished evaporating, and the thing they were inside of no longer exists. That last question has no accepted answer at all. So the paradox has changed shape. It has not gone away. The field has moved from asking whether information escapes to asking how, and how is turning out to be harder than whether. There is another line of attack that deserves mention, because it takes a very different view, and it has been pursued patiently for 25 years. Samir Mathur and his collaborators, working in string theory, have argued that the whole difficulty comes from a false picture of what a black hole is. In the standard picture, there is an empty interior with a horizon around it and a singularity at the center, and the mass is concentrated at the middle, while the horizon is just a mathematical surface in otherwise ordinary space. Mathur's proposal is that this picture is simply wrong, that it is what the true object looks like when averaged over in a way that throws away exactly the thing one needs. The proposal is called the fuzzball. The claim is that a black hole is not empty inside. It is a dense, structured object, made of the extended objects that string theory provides, filling the entire region out to where the horizon would be, with no horizon at all, no interior in the usual sense, and no singularity. It has a surface. The surface is at roughly the Schwarzschild radius, because that is where the mass makes the geometry close up. But it is a real surface made of real stuff, and radiation coming off it is like radiation coming off any hot object, and it carries the information out the ordinary way, exactly as a burning book does. If this is right, then there is no paradox, because Hawking's derivation assumed a vacuum at the horizon, and there is no vacuum at the horizon. There is something there. The equivalence principle would fail at the horizon after all, though not in the violent way a firewall fails, since the fuzzball is thought to have a structure that a falling observer might, in some formulations, pass into rather than strike. The difficulty is the counting. For very particular kinds of black holes, ones with a great deal of supersymmetry, an extreme electric charge, and no realistic counterpart in nature, the fuzzball construction can be carried out explicitly, and the number of distinct configurations comes out exactly right, matching the entropy formula precisely, factor of 1/4 and all. That was an early triumph, related to a landmark calculation by Andrew Strominger and Kamran Vafa in 1996 that counted the microstates of a black hole for the first time and got Bekenstein's number. For ordinary black holes, the kind that actually form when stars collapse, the explicit constructions do not exist, and it is not known whether they can. The program is a bet that they can. So there are at least two live views. One says the interior exists and is encoded non-locally in the radiation, and the horizon is smooth, and the strangeness lives in the accounting. The other says the interior does not exist, and the horizon is not smooth because there is no horizon, and the strangeness lives in what the object is made of. They cannot both be right. Neither has been ruled out. There is a phrase that has come into use recently for the minimal set of things most researchers now agree on. It is sometimes called the central dogma of black hole physics, and it says that a black hole, seen from outside, behaves like an ordinary quantum system with a number of degrees of freedom equal to its area in Planck units divided by 4. Evolving unitarily in time. That is all. It does not say what the inside is. It does not say how the information leaves. It says only that from far away, a black hole is a box with a definite number of states and a lawful rule for evolving them, like any other box. Almost everyone signs that now. And the space of things that it does not settle is still very wide. It is worth pausing here to say something about what all of this is standing on, because a person could listen to this and conclude that it is all mathematics with nothing underneath. It is not. Black holes are not a hypothesis. They are observed routinely, and the evidence has become overwhelming within a single human lifetime. The first strong candidate was Cygnus X-1, a source of X-rays in the constellation of the Swan, identified in the early 1970s. It sits about 7,000 light-years away and consists of a hot blue supergiant star and something invisible. And the invisible thing is heavy enough that no known object other than a black hole could account for it. It was the subject of an earlier bet between Hawking and Thorne. One Hawking lost in 1990, and he took the loss as insurance, since he had spent his career working on black holes and wanted some consolation if they turned out not to exist. Then came the center of the galaxy. Starting in the 1990s, two teams, one led by Reinhard Genzel in Germany and one led by Andrea Ghez in California, spent decades tracking individual stars orbiting the galactic center, 26,000 light-years away, through the dust that hides it from ordinary telescopes. They watched a star now called Estwo complete an entire orbit, a loop of about 16 years, swinging around something with a mass of roughly 4 million suns, packed into a region smaller than the orbit of Mercury. There is nothing else it could be. Genzel and Ghez shared the Nobel Prize for it in 2020, together with Roger Penrose, who had done the mathematics 60 years earlier. In September of 2015, the Laser Interferometer Gravitational Wave Observatory detected a signal lasting about 0.2 of a second, produced by two black holes of roughly 30 solar masses, each spiraling together and merging, more than 1 billion light-years away. The waveform matched the prediction of general relativity for such an event with a precision that is difficult to convey. In the final moments of that merger, more power was radiated in gravitational waves than all the light from all the stars in the observable universe combined. It arrived at the detectors as a wobble in the length of a 4-kilometer arm, smaller than 1,000th of the width of a proton. Hundreds of such mergers have been recorded since, and in April of 2019, the Event Horizon Telescope collaboration released an image assembled from radio dishes scattered across the Earth working together as a single instrument the size of the planet. It showed a ring of light around a shadow at the heart of the galaxy Messier 87, 55 million light-years away, produced by an object of roughly 6.5 billion solar masses. 3 years later, they released a second image of the object at the center of our own galaxy. The shadow in those images is not the horizon. It is somewhat larger because gravity bends the paths of the photons around it. But it is the closest thing to a photograph of a hole in space-time that has ever been made. And the objects in question have entropies of around 10 to the 90th, which is to say, they hold more information than every other thing in their host galaxies put together, and hold it where no one can read it. The paradox is not about imaginary objects. It is about the largest and most common repositories of information in the universe, which raises the thing that sits underneath all of this and is rarely stated plainly, which is the question of what is actually inside. General relativity gives an answer, and the answer is that the theory has failed. Follow the geometry inward from the horizon of a non-rotating black hole, and it does not lead to a place. It leads to a moment. Inside the horizon, the radial direction and the time direction trade roles. The center is not a location one could choose to avoid by steering. It is a time in the future, as unavoidable as next Tuesday. Every path, every trajectory, every possible motion arrives there. The crossing itself, for a large enough hole, is uneventful. For one of the supermassive kind, billions of solar masses, the tidal stretching at the horizon is so gentle that a person would pass through without any sensation of having passed through anything. There would be no boundary to see. Looking back, the sky would still be there, distorted, gathered into a bright ring. The light of the outside universe compressed and blue-shifted and crowded toward one direction, and it would remain visible for a while, because light can still come in even though nothing can go out. The universe would not vanish. It would concentrate. For a smaller hole, one of stellar mass, the crossing does not happen at all in any recognizable form, because the difference in gravity between one end of a body and the other becomes lethal long before the horizon, and a falling thing is drawn out into a thin stream well outside. The word for that is not a technical one. Someone called it spaghettification, and the name stuck, which says something about the tone physicists reach for when the subject gets grim. Either way, the fall inside is short. For a black hole of 10 solar masses, the time from horizon to center, measured on the falling clock, is a few hundred millionths of a second. For the one at the center of this galaxy, it is about a minute. For the largest known, perhaps a day. There is no fighting it and no slowing it, and firing engines outward makes it arrive sooner rather than later, because acceleration costs proper time, and the longest possible remaining life belongs to the one who does nothing at all and simply falls. And at that moment, the equations produce infinities, curvature without bound, density without bound. The quantities that describe the shape of space grow past every number and stop being numbers. Physicists call it a singularity, and the word sounds like a thing. It is not a thing. It is the sound a theory makes when it breaks. Every previous appearance of an infinity in physics has signaled the same thing, that a description has been carried past the edge of the domain where it applies. Newtonian gravity produces an infinite force between 2-point masses at zero separation. That did not mean the universe contains infinite forces. It meant that point masses are an idealization. Penrose proved in 1965 that singularities are not artifacts of assuming perfect symmetry, that they arise generically in gravitational collapse under general relativity. That was the theorem that earned him the Nobel. But the proof assumes general relativity is correct all the way down, and no one believes that. General relativity is a classical theory. It has no quantum mechanics in it. In the region where the curvature becomes extreme, the quantum nature of gravity must matter, and no one knows what quantum gravity says because no one has it. So the honest answer to what is inside a black hole is that nobody knows. What is known is where the theory stops being trustworthy, and that boundary sits deep inside, far from the horizon, in a region no signal will ever leave. The rotating case is stranger still. Kerr's solution, which describes every real black hole since everything spins, has an interior that, on paper, contains not a point but a ring. And beyond the ring, there are regions where the mathematics permits paths that loop back into their own past. And beyond that, there are passages that appear to lead out into other regions of spacetime entirely. This is the origin of a great many stories about black holes as gateways. It is almost certainly not real. The interior of the Care solution is thought to be unstable, so that any disturbance falling in, any light, any dust, any small amount of anything at all, would pile up along an inner surface and pinch the geometry off before any of the exotic regions could be reached. The passages are artifacts of an idealization, like the point mass and its infinite force. But the fact that the equations produce them is a reminder of how little firm ground there is once the horizon is behind. There is a further wrinkle, which is that the singularity may be a red herring for the paradox entirely. Some have argued that information loss happens not at the singularity, but at the horizon, or nowhere at all. Others have argued that what a singularity does to information is precisely the question. The disagreement is not resolved. What is agreed is this: a black hole is the only place in the universe where the two great theories of the 20th century are forced to sit in the same room. Everywhere else, they can be kept apart. Quantum mechanics handles the small, where gravity is too weak to notice. General relativity handles the large, where quantum effects average away. There is no experiment anywhere that requires both at once, no laboratory measurement that probes the seam. Except here. A black hole is a large object made of gravity whose behavior, once Hawking's calculation is admitted, depends on the quantum structure of the vacuum. Its entropy has Planck's constant in it, Newton's constant in it, and the speed of light in it, all three, which is a thing almost no formula in physics does. It sits exactly on the seam, and when the two theories are placed side by side and asked a simple question, what happens to a book that falls in, they give different answers, and the difference is not a small correction. It is total. That is why so much effort has gone into a problem that will never be measured. There is no experiment. The temperature of a stellar mass black hole is 60 billionths of a degree above absolute zero, buried under a background 40 million times warmer. The page time is longer than the universe has any use for. No apparatus that could ever be built could detect a single Hawking photon from any black hole known to exist. There are proposals for laboratory analogs, systems of flowing water or cold atoms or optical fibers that mimic the mathematics of a horizon. And some of them have produced results that look like Hawking radiation. And those results are interesting and contested. They are not black holes. So the work proceeds on paper with the paradox as the only instrument. It is a strange kind of experiment. Take two theories that cannot both be right. Push them until they contradict. Read the contradiction carefully enough, and it will say something about what is missing. And it has said things. That was not guaranteed. A paradox can be sterile. This one has been the most productive puzzle in theoretical physics for half a century. The holographic principle came out of it, and holography is now the central organizing idea in quantum gravity. The correspondence between gravity and quantum field theory came out of it. The realization that spacetime itself might be made of entanglement. That geometry might be what a certain pattern of quantum correlations looks like from far away, came out of it. Every one of those ideas started as an attempt to work out where a book goes. Consider that possibility for a moment, because it is the strangest thing in this entire account, and it deserves to be sat with. The evidence has been accumulating for 20 years that space is not fundamental. Not that space is an illusion in some vague sense, but that the smooth, continuous, three-dimensional arena in which everything appears to happen might be an emergent description of something else. The way temperature is an emergent description of molecular motion. Temperature is real. A person can feel it, but there is no such thing as the temperature of a single molecule. Temperature only exists when there are enough molecules to average over. It is a property of the description, not of the substance. The suggestion, which came from thinking about black hole entropy, and was sharpened by work from Mark van Raamsdonk and Brian Swingle, and others in the 2000s and 2010s, is that distance works the same way. That two regions of space are near each other because they are entangled, and far apart because they are not. And that if one took a quantum state describing a region of space, and gradually removed the entanglement between two halves of it, the geometry would not slide apart. It would tear. The space between them would stretch and thin and then cease to exist, and the two halves would become separate universes with no distance between them, because distance would have stopped applying. If that is right, and it is far from established, then the black hole information paradox was never really about black holes. It was about the fact that anyone was still treating space-time as the stage rather than as part of the play. But leave the theory for a while. The rest of this belongs to time. Because the question of whether the universe forgets is, in the end, a question about the far future, and the far future is where black holes stop being exotic and become ordinary, and then become everything, and then become nothing. Start from here. The universe is about 13.8 billion years old. Stars are forming, though at a rate that peaked long ago and has been declining for roughly 10 billion years. The sky is bright by the standards of what is coming. This is the stelliferous era, the age of stars, and it is the only age anyone has ever seen or ever will. It is not long, not by the measures that follow. In about 5 billion years, the sun will exhaust the hydrogen in its core and swell into a red giant, engulfing Mercury and Venus and quite possibly the Earth, and then shed its outer layers into a slow expanding shell and settle down as a white dwarf, an object about the size of the planet and about half the mass of the sun, made of carbon and oxygen packed so tightly that a spoonful weighs several tons. The white dwarf will glow from stored heat, dimming and reddening for a very long time. It will not become a black hole. It has nowhere near enough mass. The sun is typical. Most stars end that way. Only the rare heavy ones, those beginning life at roughly 20 times the sun's mass or more, collapse into black holes when their cores can no longer hold themselves up. And even that threshold is uncertain and depends on details of composition and rotation, and how much mass the star sheds along the way. Meanwhile, the galaxies drift. The Andromeda Galaxy is approaching, one of the few large galaxies that is, and in roughly 4 to 5 billion years, it will meet the Milky Way, and the two will pass through each other in a slow choreography lasting 1 billion years or more. Almost nothing will collide. Stars are too far apart. The gas will collide, and where gas collides, new stars form, and the merged galaxy will flare briefly with new light before settling into a quieter elliptical shape. The two central black holes will sink toward each other over hundreds of millions of years and eventually merge, releasing a burst of gravitational waves that will pass through everything without effect. Beyond the local group, the rest of the universe is receding, and the recession is accelerating, driven by something that is called dark energy for lack of a better name, and that nobody understands. If it continues as it appears to, then in something like 150 billion years, The galaxies beyond the local group will have passed beyond the horizon of what can be seen, and the sky will contain nothing but the merged remnant of Andromeda and the Milky Way and their small companions, alone in a dark that goes on without limit. Any astronomer alive then, examining the universe with the finest instruments, would conclude that it consists of one galaxy in an empty and static void. The expansion would be invisible. The cosmic background would have stretched into undetectability. The evidence would be gone. That is worth holding for a moment. The universe is capable of losing its own history on the largest scale without any black holes involved. What can be known depends on where one is standing. Star formation continues, slowly, as long as gas remains. The last stars to form will be the small ones, red dwarfs, which burn their fuel with an almost absurd frugality. A red dwarf, a tenth the mass of the Sun, can burn steadily for something like 10 trillion years, 1,000 times the current age of the universe. When the last of them fades, roughly 100 trillion years from now, the age of stars ends. What is left is called the degenerate era, and it is populated by remnants. White dwarfs cool toward the temperature of empty space, eventually becoming black dwarfs, dark and inert, though none exists yet because the universe has not been around long enough for even the oldest white dwarf to finish cooling. Neutron stars spinning down, their magnetic fields decaying. Brown dwarfs that never quite ignited, planets dark and cold, and black holes drifting among them. This era lasts a very long time. Its end depends on a question that has never been answered, which is whether protons decay. Some theories that attempt to unify the forces predict that the proton is not stable, that it has a finite lifetime, after which it comes apart into lighter particles. Experiments have been searching for this for decades, watching enormous tanks of water underground for a single proton among many trillions of trillions to fall apart. None has ever been seen. The searches have pushed the proton's lifetime to more than 10 to the 34th years, which is far longer than anyone once expected. And the simplest theories predicting decay have been ruled out by exactly this. Whether protons decay at all remains open. If they do, then over a span of perhaps 10 to the 36th to 10 to the 40th years, all ordinary matter comes quietly apart. White dwarfs and neutron stars and planets and dust, and everything else dissolve into radiation and light particles, glowing faintly with the heat of their own dissolution, each white dwarf shining with roughly the power of a small lamp, for a span of time that beggars description. Then even that is gone. If protons do not decay, ordinary matter persists, though it does not stay in the arrangements it has. Over timescales longer than any of these, quantum tunneling rearranges everything. Any object, given enough time, will tunnel through the barriers that keep it in its shape. Matter tunnels into its lowest energy configuration, which is thought to be iron, so that after something like 10 to the 1500th years, every remaining lump of anything has become a sphere of iron. And then the iron spheres, given still more time, tunnel into black holes on a timescale written as 10 raised to the power of 10 raised to the power of 76. A number that cannot be written out because the universe does not contain enough room for the digits. Either way, and this is the point, black holes outlast everything. They come to dominate, not because they grow, though they do grow at first, feeding on whatever wanders close, but because everything else ends and they do not. The black hole era begins, and the universe becomes a very thin scattering of dark massive objects, separated by distances that keep increasing, radiating at temperatures so low that the word cold does not begin to apply. And then, at last, they begin to evaporate. Not before. The evaporation cannot start until the universe has cooled below the black hole's temperature, and since black hole temperature runs inversely with mass, the small ones go first and the largest go last. A black hole with the mass of the Sun, once the background has cooled enough, evaporates over roughly 10 to the 67th years. It is not a dramatic process. For almost the entire span it emits, on average, less than 1 photon per century, per millennium, per far longer than that. It shrinks by amounts too small to name. It is a process of such profound slowness that nothing else in nature offers a comparison. A black hole, the mass of the one at the center of this galaxy, 4 million suns, takes something on the order of 10 to the 87th years. The largest ones known, tens of billions of solar masses, take perhaps 10 to the 100th years, and that number, 10 to the 100th, has a name. It is called a googol. It is the number that gave a search company its name, misspelled. It is the last important number in cosmology. And in every case, at the very end, the same thing happens. The black hole has shrunk to a small fraction of its original size, and its temperature has climbed, and the emission has quickened, and the quickening feeds itself, because losing mass makes it hotter, and being hotter makes it lose mass faster. The final stage takes a second or less. The last of it goes in a flash of high-energy radiation, and where a black hole was, there is nothing. Space, flat and empty and cold, with a faint spray of photons drifting away in every direction, never to interact with anything again. That flash is the last event in the history of the universe. Not the last event of a kind. The last event. After the final black hole goes, there is nothing left that can do anything. What follows is called the dark era, and it consists of an immense and increasingly empty volume containing a thin fog of photons and neutrinos and stray electrons and positrons, drifting apart forever, too diffuse to ever meet, at a temperature approaching, but never reaching absolute zero. And it lasts. There is no reason for it to stop. Now return to the question, because this is where it finally means something. If the information is preserved, then that thin, cold fog is not featureless. It is a record. Every photon in it carries, in its correlations with every other photon, the complete history of everything that ever fell into any black hole. Every star that collapsed, every planet that spiraled in, every particle of every world. And if any of those worlds held anything that thought, then whatever it thought is in there too, encoded in the phase relationships of radiation spread across a volume of space, so large that light could not cross it in any span of time, that has a name. The record exists. Nothing can read it. Reading it would require gathering every photon, and they are receding from one another faster than any signal could chase them. And the gathering would require a device larger than the region the photons occupy. And there is no matter left to build it from, and there is no one left to build it. So the universe would remember perfectly forever, and there would be no memory. Only the fact of it. A record with no reader in a room with no walls for the rest of time. If instead Hawking was right in 1976, and the field now largely believes he was not, then even that is gone. The fog is exactly as random as it looks. The past would not be recoverable even in principle, not by anyone, not by anything. The universe would have ended with its history not merely unread, but absent. The difference between those two futures cannot be observed. It never could be. Nothing in the world would look different. No experiment could distinguish them, then or now. And yet, it is not a small difference, and physicists have given 50 years to it, and the reason is worth naming plainly. It is not about black holes. It is about whether the rules hold. If information can be destroyed, then the rules are not rules, and physics is a description that works well in most places and fails in some, and there is no reason to expect that the failure stops with black holes. If information cannot be destroyed, then the universe is a lawful thing all the way down, in every regime, and its self-consistency is not a convenience, but a fact about what it is. The current answer, held with reasonable confidence, and not with certainty, is that the rules hold. That the calculations of the last decade, the islands and the replica wormholes and the page curve emerging from gravity itself, point clearly toward preservation. That Hawking was right to be troubled and wrong about the conclusion, and that being wrong in that particular way was worth more to physics than being right would have been. But the mechanism is still missing. Nobody can say how the information gets out. Nobody can say what the interior is made of. Nobody can say what happens to a thing that falls in any language that would satisfy a careful listener. The problem that opened in 1976 is, in the way that matters, still open, and the people working on it now were not born when it opened, and some of them will not live to see it close. There is one more thing, and it is a small thing, but it belongs here. There may be black holes that are already finishing, not stellar ones, which are far too cold. Primordial ones, if they exist, formed in the first fraction of a second after the beginning, when the universe was dense enough that a slight overdensity in the plasma could collapse without any star being involved. Such a black hole could have any mass at all. And if one formed with a mass of around 100 billion tons, roughly the mass of a modest mountain compressed into a region smaller than a proton, then its evaporation time would be about the current age of the universe, which means that if they formed, some of them are ending now. Somewhere, perhaps in the dark between the stars, a small hot thing is finishing a process it began before the first atom, radiating harder and harder, its temperature climbing past 1 billion degrees, past 1 trillion, and then going out in a burst of gamma rays. Nobody has ever seen one. Searches have been run for decades, and the limits are now strict enough to rule out primordial black holes as the main component of dark matter across most mass ranges, though narrow windows remain, and the question is not closed. It is possible they never formed. It is possible the early universe was too smooth. But it is a nice thought to hold that somewhere out in the quiet, the very last of something is happening, and the light of it is on its way, and no one is watching. The thing that stays with a person, after all of this, is not the mathematics. It is the strangeness of the accounting. Consider what has actually been claimed. That the amount of information a region of space can hold is set by its surface, not its volume, which means the world has fewer degrees of freedom than it appears to. A black hole is the densest possible storage, and it stores on its skin. That the interior of an old black hole is not a place, but a pattern in radiation already gone. That entanglement and geometry might be the same thing wearing different clothes. That space might be what a certain kind of correlation feels like from the outside. None of that was the goal. Nobody set out to discover that space is emergent. They set out to work out where a teacup went. It is worth saying something about the people, because the problem has outlived a number of them, and that is part of what it is. Jacob B. Kenstein, who was 25 when he suggested that a black hole has entropy, and who was told by nearly everyone that he was mistaken, lived to see the idea become the foundation of an entire field. He died in August of 2015 in Helsinki, where he had gone to give a talk. He had spent 40 years on the consequences of a thought he had as a student. Joseph Polchinski, who wrote the firewall paper and thereby broke a resolution that many had considered final, described the result as one he wished were not true, and spent his remaining years trying to find the way out of it. He died in February of 2018. The islands appeared the year after. Stephen Hawking died in March of 2018, having spent almost his entire working life on a problem he identified, argued for on one side for 28 years, publicly changed his mind about, and never solved. His final paper, submitted days before he died, was on a related question. He is buried in Westminster Abbey between Isaac Newton and Charles Darwin, and the stone above him carries his entropy formula. The one that says the entropy of a black hole is a quarter of its horizon area in Planck units. It is a strange thing to put on a grave. It is also exactly right, in the sense that it is the sentence that contains the whole problem, and the problem is what he left. There is a way of thinking about this that has nothing to do with grief and is perhaps the more honest response. A person works on a question for 40 years and does not answer it. That looks, from a certain angle, like failure. It is not. The question is better formed than it was. The tools built to attack it have reshaped a field. The thing that was mysterious in 1976 is mysterious in a completely different way now, at a completely different depth, and getting from the first mystery to the second required everything. Physics does not usually work by someone solving a problem. It works by a problem being understood well enough that it turns into a different problem, and that one into another, and somewhere down that chain, the world looks different than it did. The information paradox has been running that process for half a century, and it shows no sign of finishing. And the things it has produced along the way are worth more than the answer would have been. There is another thread worth pulling, briefly, because it is one of the odder consequences, and it connects to how fast a black hole works. Yasunori Sekino and Leonard Susskind conjectured in 2008 that black holes are the fastest scramblers in nature. Scrambling means taking information that was localized, a bit sitting in one place, and spreading it so thoroughly across a system that no measurement of any small part of the system can find any trace of it. Every system scrambles eventually. Stir cream into coffee, and the pattern of the cream spreads until no spoonful reveals where it started. What Sekino and Susskind proposed is that no system scrambles faster than a black hole, that there is a fundamental speed limit on the spreading of information, and that black holes sit exactly at it. The scrambling time for a black hole is remarkably short. It goes roughly with the size of the horizon multiplied by the logarithm of the entropy, and for a black hole of stellar mass, that comes out to something like a millisecond. A bit of information dropped in is spread across every degree of freedom on the horizon in less time than a heartbeat. 10 to the 77th degrees of freedom, mixed thoroughly, in a few thousandths of a second, which is a peculiar picture. From the outside, and if complementarity or something like it is right, a thing that falls in does not simply vanish. It gets smeared across the horizon, spread and mixed and thermalized at a rate no other object in the universe can match. And then it sits there, encoded, unreadable, for 10 to the 67th years. And then it comes back out one photon at a time into a universe with nothing left in it. There is a related idea, from work by Susskind and others in the 2010s, that even after the black hole has scrambled everything and reached equilibrium in every measurable sense, something inside continues to change. The interior wormhole in the geometric picture keeps growing longer, not for a while, for an enormously long time, far longer than the scrambling time, far longer than any thermal timescale. The quantity that keeps growing is thought to correspond to something called computational complexity, roughly a measure of how many elementary operations would be required to build the quantum state from a simple starting point. Entropy saturates quickly. Complexity does not. It grows and grows, long after nothing else is happening, until it too finally levels off at a time so distant that the exponent has an exponent. Nobody knows whether that picture is correct. It is one of the more speculative corners of the subject, and it should be labeled that way. But it suggests something that is hard to shake, which is that a black hole that has been sitting quietly for 100 billion years, unchanging in every way anyone could measure, is not doing nothing. It is doing the only thing left in the universe that is still going on. So the picture, assembled, looks something like this. A star burns for 10 million years and runs out of fuel and falls in on itself. And in the falling, it sheds every distinguishing feature it ever had. Every irregularity radiated away as gravitational waves in a fraction of a second, until what remains is a surface of impossible smoothness described by 3 numbers and nothing else. Everything the star was, its composition, its history, the particular way its convection cells churned, the specific arrangement of every one of its atoms, is now on the other side of a boundary that has no substance and cannot be crossed backward. The boundary is not a barrier. It is a direction. It is the statement that outward has stopped existing. Around that boundary, the vacuum, which is not empty and never was, does what vacuums do near horizons. It glows faintly, at a temperature so low it is scarcely a temperature at all. The glow carries away mass, and the mass carries away, in some way nobody can yet describe, everything the star ever was, spread across the outgoing radiation in correlations so fine that reading them would require a catalog of every photon, and a computer the size of a galaxy and knowledge of a theory that has not been written. And the glow continues for 10 to the 67th years, and then it stops, and there is nothing there. That is one black hole. There are perhaps 100 million stellar masses in this galaxy alone, and one very large one at the center, and there are 2 trillion galaxies within the reach of the deepest surveys, and every one of them has the same arrangement, and every one of those holes is doing the same thing, quietly, at the same imperceptible rate, and will keep doing it long after the last star has gone dark. The universe is mostly, in duration, an affair of black holes evaporating. Everything that has ever happened, all of the stars and all of the planets and all of the light, is the brief opening of a process whose main body is a slow dark exhalation, lasting a googol years, and whose ending is a scattering of photons that never meet. And through all of it, the question stands: does the record survive? The answer appears to be yes. It appears to be yes in a way that nobody expected and nobody can yet explain. It appears that the universe keeps every receipt, including the ones it burned, including the ones it dropped through the floor of space itself, and that it keeps them in a form so thoroughly scrambled that keeping and losing become almost impossible to tell apart, except in principle, which is where physics lives. There is a kind of comfort in that, and it is not a false one. It says that nothing that has ever happened is undone, that the shape of a thing persists in the correlations of the radiation long after the thing itself has stopped, that the universe is not in the business of erasing. And there is a kind of loneliness in it too, and that is not false either, because a record no one can read is not a memory. It is only a fact. The universe would remember everything and know nothing forever, in a dark with nothing in it. Perhaps both are the case. Perhaps that is simply what it is like to be a lawful universe with no one required to be watching. The stars are still burning for now. The sky overhead still has light in it, and will for a very long time by the standards of a life, and no time at all by the standards of the thing being described. Somewhere near the center of this galaxy, 26,000 light-years away, 4 million solar masses of collapsed geometry is turning slowly in the dark, radiating at 60 trillionths of a degree, absorbing more from the cold background than it gives back, growing imperceptibly, waiting for a universe cold enough to let it begin to fade. It will wait 100 trillion years for that. It will take 10 to the 87th years to finish. And everything it has ever swallowed, every star that wandered too near, every cloud of gas that lost its footing, is in there, or is somewhere, held in a form that will one day drift outward into a dark that has stopped keeping time. That is not a tragedy. It is only the shape of things. The dark is very old and very patient, and it holds what it is given, and it does not appear to be in the business of losing anything at all. This channel is here for those who like to fall asleep somewhere very large. If the quiet suits, a like helps others find it, and subscribing means the next long dark will come to you. There is no need to do it now. It will keep. Rest well. The stars will manage without anyone watching, and the black holes will keep their long, slow accounts, and none of it will finish for a very long time. Good night.